Greetings, Westmont Algebra 2 students. This is Mr. Earth here. So, as I mentioned in class, I thought I would just make a quick video showing you what the expectation is for what your GeoGebra homework should look like with the cubic. So, if you'll notice right now, I've got GeoGebra running right here. So, and what you should have is at the top there should be a function here. If you're not used to function notation, this f of x, the little f parentheses x thing, just think of that as being y. We'll talk more about the function notation later, but this is what's being graphed right now. Notice it's a cubic because the degree is 3 right there. If you can see that, degree is 3. So, and right now it's the cubic 1x cubed minus 3x squared minus 6x plus 8. And over in the graphics window, we can see here's our cubic. And you'll also notice that the x-intercepts are marked. So here's R1, R2, and R3. And also, if you'll notice back over here in the number section, so the a, b, c, d, this is from our cubic equation, ax cubed plus bx squared plus cx plus d. There's the a, b, c, d right there. And it also is giving us the values of R1, R2, and R3, or in other words, the roots of this cubic. These are the numbers that when we plug it in, will make it be 0. And notice that's why they're showing up as x-intercepts over here in the graph, because the y-coordinate is 0 when we plug them in. So far so good. It's got this kind of curvy nature to it, it being a cubic. What we need to have happen is that if you take this R1 and grab it and move it. So I switched right over here to move mode. That's the little cursor right there. Now if I grab R1, and notice that over in this section over here, it's going to highlight R1 when I grab it. When I grab R1, I can move it over and drag it to some other spot too. Now my graph is going a little bit off the page there, so if I need to, I can switch to this mode, the Move Graphics view, and drag the y-axis down a little bit. So now I can see the full nature of the graph. Let me switch it back over here, back to the Move view, and notice when I changed it to 2, the graph changed. The a, b, c, and d changed, so now it's graphing 1x cubed minus 4x squared minus 4x plus 16, and that's the graph that has these 3 x-intercepts. So what you should be able to do is move any of the x-intercepts to any value that you want. And as you do it, now I'm moving it to some weird fractional decimal value, so you can see it's changing all these. But as you move it, your cubic should actually move and become different shapes. So that's how you'll know that you've done it right, is that you can actually grab the individual x-intercepts, move them around, and the cubic graph moves around with it. And so you should have that on the graph, and you should have some crazy... Now your equation is not going to be quite the same as mine unless your x-intercepts happen just by coincidence to be exactly in my spot. But when I test your submission, I'm going to move these and make sure that however you move them, the graph goes with it, and those really stay as the roots. Alright, so that's what your homework is, and good luck. If you have any questions, feel free to email me. Hi guys, one little addendum to that, something I forgot to add, is that I just wanted to point something out. So notice, let's say you've moved it around, and now you've got some crazy decimals for your roots. You're like, oh man, I don't want that, I want it on nice whole numbers. So sometimes you can grab something and move it to be, and it kind of clicks into place, so it's exactly 1, and maybe I can... Let's see, I'm going to take the R3 and move that to like -1, trying to hit it at negative, there we go. So I'm looking over here at this side and say, alright, my R3 is -1. Let me take the R2, maybe move that to 3. It's hard to get exactly on it. Almost had it, there you go. So I can see my R1 isn't quite at 1, it's a little bit off. So maybe I can take it and move it just a smidge, there we go. So now I've got my R1 exactly at 1, my R2 at 3, and my R3 is at -1. And I can look over here and see those are nice whole numbers, and I can look at, I'm still not quite at nice whole numbers, because look, my constant's at 3.01. I thought I was at whole numbers, but it turns out one of these numbers isn't quite whole, it's just past the decimal expression of what we're displaying on the screen. So how can I get exactly whole numbers? Well, one thing I forgot to point out is that you don't have to just drag these values graphically. You can actually come over here, open them up, and edit them. So what I did is I double-clicked. So I'm going to R1, I'm going to double-click it, and let's put R1, I don't know, exactly at 2. So I'm going to backspace over the 1, type in a 2, and push Enter. And so notice R1 moved to 2, and now it's really exactly at 2. Let's take my R3 How about I move that to, I'm sorry, the R2. Right now it's at 3. I'm going to backspace over the 3, put in a 4. So I'm changing it numerically here on the algebra window rather than dragging it around the graphics window. So I'm going to push the end. I've got R2 equal to 4. I'll push enter. So now it moved over to 4. And notice this R3 must not be exactly at -1 because I can still see some decimal versions over here in the function. So I'm going to go to R3. I'm going to put it exactly at -1. Push enter. And now, even though we didn't see anything graphically change here, I can come over here to the function side of things, and I can see that, in fact, everything is nice whole numbers, or at least displaying as whole numbers. 1x cubed minus 5x squared plus 2x plus 8. So if you're ever curious, hey, what is the equation of the cubic that goes through the points on the x-axis 2, 4, and -1? Or another way to say that is it has roots at 2, 4, and -1, or intercepts the x-axis at 2, 4, and -1, or an equation if I plug in 2, or plug in 4, or plug in -1, will come out to be 0. There it is. Of course, your goal, and this is part of your homework, is figuring out how in the world do I come up with a formula for A, B, C, and D that I can use for my ax cubed plus bx squared plus cx plus c to get this to come out. It's not always going to be 1, -5, 2, and 8. It only came out to be that for these particular R values. So, okay, well, hopefully that clarifies things a bit, and good luck with the homework. Hi, folks. This is Mr. Earth again. So, I thought one thing that it might be interesting to try is to actually look at our graph that we had and actually do something manually with it, just to kind of double check out to make sure the computer isn't lying to us. So here's our equation, and I just went ahead and hand wrote it here. Now don't forget, we've got these, supposedly, this is the equation that has a graph with these 3 roots right here. So that, well, let's actually check out to see if this works. So how would we check out to see that this equation is actually correct? So what we're going to do is, let's just grab this root right here. So that's our R1, which supposedly is at x equals 2. It actually says over here that R1 equals 2, and we can take a look over here and say, okay, it's crossing right at 2. So let's take x equal 2, plug it into the equation, and see if it really is a root. Because if it is a root, that means when we plug in x equal 2, the answer should come out to be 0. We should get y equals 0 if this really does cross at 2. So let's see what we get. So we plug in x equal 2, so we just start substituting. So instead of x cubed, we say 2 cubed minus 5 times 2 squared plus 2 times 2 plus 8. Well, 2 cubed is 8. Here, this one might take a little bit of thinking about, right? Because some people might say, oh, 5 times 2 is 10. I got to square it's 100. But we got to remember order of operations. 2 squared comes first because it's an exponent, right? Exponents come before multiplication. So 2 squared is 4, and 5 times 4 is 20. And then we do the 2 times 2 is 4 plus 8. So now we just have to add these up. I think it's actually easy to add this way. 8 and 8 is 16. Plus 4 is 20, and then 20 and minus 20, hey, that's 0. It checked out. It really is a root. When we plug in 2 into this formula, it comes out to be y equals 0, which means when you graph it as a point, you'd be graphing 2, 0, which is right on the x-axis. That's the x-intercept. All right, so it works for x equal 2. Well, that was our first root, our R1. What about R2? Might as well check that out while we're at it. So that's the x equals 4. So this time I went back to our formula, the x cubed minus 5x squared plus 2x plus 8. By the way, I know on the computer program it actually puts a 1 right here in front of the x cubed. I left it out. You don't really need to write the 1 there. I just wrote it as x cubed. So we go over here. I'm now replacing all the x's with 4. So it's 4 cubed minus 5 times 4 squared plus 2 times 4 plus 8. Well, what does that come out to be? Well, 4 cubed 64, again, same sort of deal. 4 squared 16, 5 times 16 is 80, 2 times 4 is 8, plus 8. Well, let's see if we can add this up in our heads. 8 and 8 is 16, 64 and 16, oh, that's 80. I'd like to do the positives first, right? So we get the 80 minus 80, comes out to be 0 again. And lastly, let's check the third one. We got x equals -1. This one's a little tricky. You got to watch your signs here, your plus and minus. So we've got a -1 cubed, always the same function right here. -1 cubed minus 5 times -1 squared plus 2 times -1 plus 8. Well, -1 cubed, a negative cube, because the exponent's odd, is going to be negative, so that's going to be a -1. Here, a -1 squared becomes a +1, so this is going to stay a -5. 2 times -1 is -2 plus 8. So again, we just kind of add up the I'll do the negatives first this time. -1 and -5 minus 2, that's -8. Plus 8, it's 0. Hooray! So all three of the roots, this alleged roots, we manually checked out according to the equation that GeoGebra was telling us. Remember, GeoGebra came up with this equation, right? This x cubed minus 5x squared plus 2x plus 8. It came up with it based on what you guys had to do for homework to program the ABCD. This is the ABCD it came up with. When we actually plugged in the values manually, indeed, they always came out to be 0. Now you might think, well, wait a second, Mr. Earth. Maybe this function just always comes out to be 0, no matter what we plug in. Let's do one that we think is actually wrong. So, what about x equal 1? Does that work? So we try it out. I just made up x equal 1 to try something out that wasn't one of these three answers. And in fact, if you plug in x equal 1, it comes out to be 6. Which is basically saying on this graph, if you actually go to x equal 1, this spot above the 1, it's x equal 1, the y coordinate is 6. So it's not on the x-axis. The y didn't come out to be 0. It's 6 higher up than that. So this is actually the point 1, 6. It did not come out to be 0. So it looks like, indeed, this equation, it matches these three roots. So just thought I'd show you manually what's kind of going on there. One last thing I should point out. So these three numbers worked. We saw that x equal 1 didn't work. The ones that worked were 2, 4, and -1. 1 didn't work, but could there be some other number that worked? The answer is no, because of the fundamental theorem of algebra, right? So we learned that since this is a polynomial and the degree is 3, there can be at most 3 different solutions for any value. In this case, it's roots. So there's 3 roots at most at this, and here they are. So any fourth number that we could ever think of will never come out to be 0. Alright guys, that's it. Good luck.